Hi, welcome back. Today we're going to be taking a look at U substitution again, but this time we're going to be taking a look at it with trigs. Now before we begin, this should be a 2 right there. Before we begin, we're going to take a look at a substitution problem that we haven't seen yet. And when we take a look at problem number 1 right here, this is just like a little bit of a warm-up for us. If I wanted to integrate this one, just like yesterday, this is a composite function. So when we take the antiderivative, we're going to be using U substitution. And so for this one, we're going to let U equal the inside function. And that's going to be this 1 plus, and I'm going to bring that x up, x to the negative 1. The derivative just becomes, that's 0, and this becomes negative 1 x to the negative 2, which is negative 1 over x squared dx, just like we did yesterday. And solving for dx, we're going to get negative x squared du. Remember, we're just going to multiply there. If I were to rewrite my integral, we would now get u squared, because remember this 1 plus 1 over x is just u, times 1 over x squared, and then our dx is just this negative, I'm replacing my dx now, this negative x squared du. And notice the x squareds cancel. We said yesterday if they don't cancel, you did something wrong. Go back and fix that. Simplifying this now, this becomes, don't forget the negative. We get negative u squared du. And if we integrate that, we get negative u cubed over 3. That's our rule for antiderivative plus your constant of integration. And then just plug in your u. Don't forget to replace your u. U we said was this 1 plus, and again, I'll make this 1 over x now, cubed over 3 plus c1. And there is our antiderivative. Ooh, that's kind of a nasty one right there. So let's talk about trigalicious functions. From yesterday, we took the antiderivative using U substitution. And in many problems, our U is going to be the inside function. That comes from the idea of a composite. Remember, this is what we need to replace. We need to replace all the x's and the dx. So we're either going to replace them or we're going to cancel them. So let's take a look at number 1. Here we have our sine function. Notice this is composite. So this says I have to use U substitution. I have an inside rule here. So my u is going to be 4x. Our du becomes 4dx. Solving for dx, we get dx equals du over 4. So when I rewrite my integral, I get sine of u du over 4. Now notice, no longer composite because I don't have anything inside. A composite, remember we said it's a composite if there's anything attached to the x. Like here I had that 4 times x, so that's composite right there. If it was just u, that's not really composite, that's just my variable. The 4, be very careful with this one. I'm going to write this as 1/4 sine u du. And now I have to think, what function's derivative was sine? That's on our list, and that's negative cosine of u plus c1. And then the last thing we're going to do, again, replace u. And I know what you're saying, Mr. Warren, nothing can replace u. All right, our u here is 4x, so we're just going to put that in and then add our constant of integration right there. So let's try number 2 here real quick. Again, this is a U substitution. Now notice, this is a weird one. We got that 3x squared and cosine of x cubed. This right here is composite. It has an inside, so that's going to be my u. U is going to be x cubed. Du, 3x squared, dx, and I can say my dx is just going to be du over 3x squared. So when we write this, we get 3x squared. Now that didn't cancel, but we'll talk about that in a second. We get the cosine of u, and dx, remember we're replacing it with this du over 3x squared. Now remember, we're either going to cancel or replace all of our x's. So we replace these x's. Now we're going to cancel the 3x squareds. Those are going to cancel, and what we're left with is just cosine of u du. And what function's antiderivative is cosine? Well, Sorry, what's the antiderivative of cosine? That is sine of u plus c1. The derivative, and that's because the derivative of sine is cosine. So my final answer, replace your u, x cubed plus your constant of integration right there. Ta-da! Okay, let's start. So if you want to pause it right now, go and try number 3. You can. I'm going to go and keep going. So for number 3, same thing. It's composite because I have an inside function. This would be like chain rule for us. So our u is going to be 7x plus 5. Our du is 7 dx. So dx is just du over 7. And when we rewrite this, we're going to get cosine of u du over 7. Now, I'm going to rewrite this because I don't like my 7 right here. I'm going to write this as a fraction, 1/7, because it's on bottom, it's a fraction. Cosine of u, don't forget your du, your differential. And remember, what function's derivative is cosine? That is sine. So we get 1/7 sine of u plus c1. Replace your u, we get 1/7 sine. U is 7x plus 5 plus c1, and there we go. Now we can check this. Remember, this is my function. The inside, that's my derivative right there. That's my derivative. So I can check it. So if I take the derivative of my function, I should get whatever is inside of my integral there. So we can go ahead and do that. Take the derivative of 1/7 sine 7x plus 5 plus c1. If we take that derivative, this becomes 1/7 chain rule cosine 7x plus 5 times chain rule 7 plus, and that just the constant becomes 0. 7's cancel, and we are left with exactly with what we started with. So it works out really nicely for us. So let's take a look at another example here real quick. Oh no, a hard one. This should be secant squared of x. Sorry about that. There we go. We'll fix that right there. When we solve this one, again, this is a composite. We really can't see it, but this tangent of x is inside. Another way I can look at it is, if you notice in U substitution, we are using these derivatives to cancel, right? For example, if I take a look at example number 2 up here, notice the derivative of the inside function is exactly the same as my outside function. And yesterday we talked about this using our chain rule. You can take a look at the video on that one. So the derivative of the inside is always going to be on the outside function. And that's exactly what we have here. If I took the derivative of tangent of x plus 1, that is secant squared of x. And that's exactly what's on the outside. So that's another way we can determine what u will be. So we're going to let u equal the tangent of x plus 1. Its derivative, secant squared of x, dx, from yesterday. And then dx would just be du over secant squared of x. So when we write our integral, we're going to have this 2 secant squared of x times u du over secant squared of x. And notice those insides are always going to cancel. That derivative of the inside should cancel with the derivative with the outside function right there. And what we're left with is 2u du. And when we integrate that, we get 2u squared over 2 plus c1. Of course, the 2's cancel, and I can replace u with tangent of x plus 1 squared plus your constant of integration right there. All right, we're going to stop the video here, go on to part 2, and we'll take a look at some more examples, some more fun ones for us. See you then.